Good day to you all, guys. So this question is we should verify Tellegen'S theorem as applied to network theorem. Okay, so to verify it, we are taking this question as example. So dive to the solution. These three resistors are in parallel, you can see. So we're going to be having resistance R2, R3, R6, that is R2, R3, R6 are all in parallel, or they are connected in parallel. So connection for parallel is what? 1 over Rp equals to 1 over R1 plus 1 over R2 plus 1 over R3, and that is this we have here. We'll find the LCM. The LCM here is what? 6. 6. They can only go in 6, and there's no multiplication. Okay, just find the LCM. Then how many times can 2 go in 6? 3. 3 go in 6, 2. 6 go in 6, 1. Then we can multiply and have 6 over 6, which is what? 1 ohms, and this is 1 over Rp. So this implies that 1 over Rp equals to 1. Then if I cross multiply to get Rp, that will be Rp equals to what? 1 ohms. Rp means resistance in parallel. So then the circuit diagram becomes like, this will become 1 ohm. Then we're going to have the 11 ohm, 1 ohm, and we're going to have this connection, and we're going to have this voltage and this voltage source. Then therefore the next thing as well is this and these are both in what? Series. So R11 ohm, R1 ohm are connected in series. That is RT equal to 11 plus 1 ohm, and that is 12 ohm. So then the circuit diagram will change. This will change to become 1, which is 12 ohm. Then we can have 40 and 12 continuously. Then the next thing is we're going to take now we got this. To not get the current, we're going to apply Kirchhoff. That is Kirchhoff current law, and we are taking direction of this current as what? As negative. Like we are taking it anti-clockwise. So when we are taking it anti-clockwise, and the law the rules are anytime current flows in your direction, it is negative. And when you are taking your Kirchhoff current law, wherever the direction comes out for this particular source, it is still the same thing. So the way I'm taking direction like this is negative, this is positive. That means to be plus 40, this will be plus 12, and this is going the same direction with this current, that is, it will be negative. So that would be apply Kirchhoff current law and taking current in the anti-clockwise direction. You can say, hey prof, can't we take it in clockwise direction? We can take it in clockwise direction, and that will similarly give us minus 40, minus 12, and plus 12. But now we are taking it anti-clockwise for easy calculation. So we're going to be having this one here, and that will be 40 plus 12, 40 plus 12 minus 12i equal to 0. That is, if you are taking it in the anti-clockwise direction, so we're going to be having like this, and that will be plus 40 plus 12 minus 12i equal to 0. If it is like this, it will be minus 40, that is, you can see minus 40 plus 12i minus 12, but we're taking this anti-clockwise. So we're going to be having, then that will be 52 equals to 12i, that is, bring this onto this side. Then I will now be equal to divide both side by 12, and we're going to have as 4.33. So leave it in 4 decimal for easy calculation and standard note. Okay, so using current divider rule to obtain each individual current flowing through each of the resistors connected in parallel. That means we are using current divider rule to get each of these what? Current flowing through this, because they are connected in parallel. So that will be the total current flowing times each individual. So therefore we're going to be having, so the diagram circuit always the calculation is always in the current for each individual, say I2 or I1 you want to calculate, times the total equals to the total times 1 over that particular one of this divided by their each one over, because they are all in what? Parallel. Do you understand? If it is for 2, to just simply be R1 over R1 plus R2, but if it's for 3, it's going to be 1 over R, the individual one. So therefore this is a circuit analysis diagram. So that will now be for this for the current flowing through this 2 ohm, it will now become the total current times this 1 over R2 all over 1 over R2 plus 1 over R3 plus 1 over R6. So we're going to be having this as I1 equals to IT, which is now 1 over R1 over 1 over R1 plus 1 over R2 plus 1 over R3. Then that will be I1 equal to, the IT is 4.33 as we got here, and that will now be 4.33 times 1 over R2 all over this, and this. Then calculating this, we have this answer. Same thing for I2 will now be 4.3, that is the total all over what? Times 1 over R3, that is for that resistor R3 here. Then all over the total each of them, we have this same thing for I3, this. But remember that this one is connected in what? Is connected in series. So therefore, the connection in series is different from this. Now, current that flows through a series resistor is always the same as the total. Okay, so the current flowing through each of these are same 4.33, which is the total we got here. So now let's move and let's be fast because I don't intend on making this video long. Since the 11 ohm of I4 is in series, this means the current flowing through it is the same as total current. So therefore therefore I4 equals to what? 4.33. So now is to calculate each resistors and the voltage, each individual voltage power. So the formula is the power developed equals to power delivered equals to power absorbed, and the subtraction of power delivered minus power absorbed must be equal to 0. You know Tellegen'S theorem, the first state that the total power, the first rule state that each of them, so the rule states that, or the law states, Tellegen'S theorem states that for a lumped network, the algebraic sum of the instantaneous power in all the branches at any instant or point is 0. And also the algebraic sum of power absorbed by all the independent sources of the network is equal to the sum of the power absorbed in all the branches. So this rule and this statement or this law tells us that the total summary of each individual power and minus this one will give us 0. Okay, so therefore, and they are equal to each other. So therefore, power delivered is equal to IV, that is delivered, and the power delivered is that one in voltage. So power delivered is equals to IV of 40 plus IV of that 12. Then we have the I already passing through, which is the total. We have this, and the power that is for that 12 ohms, we also have it as what? As this. Then we have this value. So total power delivered is this in what? Then power absorbed equals to I square R. So we're going to be calculating each individual current that is flowing through the resistance. So let's see that the current flowing through the resistance of R2, R3, and R6 and R11 are individually different. Okay, so let me quickly show you. So here we can see that if current is flowing through like this, it starts from here because this has lesser resistance. So we're gonna have I2, I3, I6. So that is I1, I2, I3, I4. So the current flowing through, as you can see, is 2.166 from here. 2.166, and the current flowing through here is what? 1.444, and also from here is 0.72. So you can notice that is 0.7. So you can notice that their resistance is small, but the current that flows through are more bigger. Do you now see that the resistance and the current flowing through 6 ohm is 0.722, while this one is having bigger current? That is why current, this one will be I1. Do you understand? So now this one we have the lowest resistance by the bodies. So here we can see that these are the current flowing through. So the current flowing through 2 ohm resistance is 2.166 or 166 ampere, and the current flowing through this is also 1.444 and 0.72. Do you notice that the currents are smaller but it's bigger for here, which is for 2, which means that this 2 ohm has less resistance. That means the current will be more bigger, but this one is in series, so the current will be very same, equivalent to the total, which is now 4.33 ohm. So you should know that the current flowing through each individual resistors are different. So we're going to be using them to calculate the power, like I showed. So therefore here the power each individual of this absorbed for RC is now 2.166 times 2. That ohm, we have this of 3, we have this of 6 ohm, we have this of 11 ohm is now we have this. And the power total absorbed is what? Everything we had, the total power absorbed together, which is 9.383 6255 588 like this, and total power is this. Now we need to approximate it to decimal because ideal power absorbed is always a bit lower to the total power delivered. There usually used to be a very tiny fragment that will remain small but is considered as 0. So if I minus this directly from this, I'm going to have like 0.000001 something. So that will be 1 plus, that will be very small, and that is just similar to 0 for calculation and proof and process. So we can have this as what? Approximate. So it's better to approximate to decimal place, and we can have this as power delivered, power absorbed, and we can have this as power delivered minus power absorbed equals to 225.3333 equal to 0 watt proved. So I hope this is very helpful for you to master verification of Tellegen'S theorem. So I want to share with you here that you must make sure you write appropriate writings explanation if you have to use this, and appropriate circuit diagram. And I love you all. I want to become more better and succeed in your academics. All right, good day to you all.